Hey, how's it going? Welcome back. Hopefully you've got your project set up in whichever environment you want to work with and you're good to go. In this video, we are going to look at drawing lines. We're going to look at just a straight up algorithm, and then we're going to look at the Bresenham line algorithm, which depending on your system may speed things up, maybe not. Who knows? Now, before we get into that, I had a quick look at the numbers on the poll, and as of recording this right now, the votes stand at OpenGL 3 votes, Vulkan 4 votes. So it's split right down the middle, and I've decided, I guess I'm going to go with Vulkan. Now, don't worry too much if you feel like this excludes you. It absolutely does not. If you go back and if you want to use OpenGL, just have a look at the OpenGL library and then watch this video, and you'll see that they're actually very similar. The process we're following, all we're doing is calling high-level functions to set pixels, and you could follow along here doing offline rendering using Turtle if you want. And you're laughing because you know what Turtle's like, but we can do it totally. Anyway, so let's get into it. Let's draw some lines. Let's go. All right, so let's have a look at line drawing. Before we look at line drawing, I'm just super quickly going to look at setting pixels on the screen. So let's say we have a screen. It has a width of 640, height of 480. Just pick those numbers out of the blue. So the top left corner will be pixel 0, 0. If we go across, we're now at pixel 640 with y0. Go down, we have 640, 0, 480. Okay, excellent. Now, I've got this pixel, and this pixel, I'll just put it here, is at some x, y coordinate. Now remember, although we're looking at this pixel on the screen, it is not represented in a two-dimensional array in memory. Rather, it's a one-dimensional array, which is slicing around and coming back on itself. So if I wanted to set this pixel, I would have to, if I had a little pointer and I imagined walking all the way across, I'd go, okay, scan all the way across, and then down to the next line and keep going. Okay, so each of these lines is 640 pixels across. And how many lines are there? Well, we'll have to go down by y lines in order to get to the correct line. And then once we're on the line, we will step across from the left of that line by x pixels. And so the concept is to set the pixel position of an xy coordinate. That corresponding position within the array will be the screen width times the y coordinate, because that's all the scan line skips that we're doing, plus that x coordinate, the little offset on the end there. Now, this is if our system is set up horizontally, which by the way, our Vulkan system is. Our OpenGL system is set up vertically, but the same principle applies. So to have a vertical system, then we'll have the pixel position of xy. This would be, okay, the skips are happening vertically. So we take the height times the x plus the y coordinate. Now, what's the benefit of this? In a horizontal pixel addressing system, horizontal lines are really fast because you're just stepping directly to the next memory location, which means you get cache adjacency, but also it means that you can use AVX and you can set 8 pixels at a time, and that's better. In a vertical system, of course, vertical lines are faster, and that's really useful if you want to do a raycasting system or something. Now we're going to we're going to be doing polygon rasterizing, in which case it doesn't actually matter whether we use a horizontal or vertical system. Okay, so with that out of the way, what about drawing lines? Well, let's look at a naive implementation first. So naive line. There are two scenarios. One scenario is where we're drawing between 2 points, call this x1, y1, and the point we're drawing to is x2, y2. This scenario is what I would call a shallow line. That is where the dominant axis, the dominant direction, is the x, because the change in x given by x2 take x1 is greater than the change in y given by y2 take y1. Now, that's one scenario. The other scenario is a steep line where the y separation is the greater of the two. So we'll have our x1, y1, x2, y2, and similarly our x difference. Yeah, okay. So here's basically how it goes. We'll start off and we'll say, okay, let's start with a variable x, which is the start point, and a variable y, which is the start point. Okay. And then we'll enter into a loop where we'll plot the xy point. We'll set that on the screen. And then there are two scenarios. If we're drawing a shallow line, then our x will be our independent variable, and we'll just set that increment it by 1, and then our y will be our dependent variable, and we'll increment it by dy dx. I guess we don't need these colons anyway. So that's the shallow line scenario. Once we do that at the bottom of the loop. We pop back, plot the next point, and just keep going. Keep going until x is equal to x2. In the steep line, we increment y by 1. So y is our independent variable, and x is our dependent variable. So we increment it by dx. So we plot the point and then increment as necessary. And we wouldn't have this all in the one function, but what we would have is a function to draw a shallow line, a function to draw a steep line, and we'll jump to either of those based on the condition around the x or y separation. Okay, so this is fine. I mean, it's very intuitive, but there is the issue that we're dealing with floating point numbers, which sometimes they're good, sometimes they're bad. But the fact is, not all math operations are equal. And just because our CPU supports floating point numbers, that doesn't necessarily mean they're fast. We'll get into performance measuring in the practical part of this. But a popular algorithm for drawing these lines quickly is Bresenham's line algorithm. Okay, so imagine that we have a line. Let me just sketch this out. So I'll say, okay, we'll have a line x1, y1. It's a little dodgy. And we have an intercept here, so I'll just call this 0b. Okay, so what we've got is the true value is, so y will be the true value. That'll be dy dx times x plus b. Okay, and we're going to work with this. This is our, so we'll use this to form an error function, an objective function, which we want to find the root to. So multiply everything by dx. We have dx y equals dy x plus b. Then the question is, okay, well, what's b equal to? Well, if we pop over to our diagram here, we can see that b is the intercept, and we have that it's on the slope. So we have b minus y1, so rise over run, or fall over run in this case, over 0 minus x1 equals y2 minus y1 over x2. minus x1. Okay, good. So let's just multiply. No? Yeah, actually, I changed my mind. Multiply both sides by negative x1, and then we get b minus y1 equals x1 minus x1 y1 minus x1 y2 over x2 minus x1. Then add y1 to both sides. So then we'll get this under a common denominator by multiplying the top and bottom by x2 minus x1. So this gives us so there you can see I've multiplied and divided by x2 minus x1 to get this all under a common denominator. Now, if we were to have a look at this, we have, what is it? x2, y1, which doesn't occur here, but then we have negative x1, y1, which will cancel out this term here. And then if we have a look here, this comes out to, what is it? x2, y1 minus x1, y2. But then, don't forget, up above here, we multiplied everything by dx. So then if I were to put these actual numbers in here, for dx, we have x2 minus x1. And then for dy, and then for this expression here, we have this b, but it's b divided by dx, really. Then we're multiplying by dx, so that'll cancel out. So I'll just put this in brackets to show that it's a constant term. It doesn't depend on x and y. That is x2, y1 minus x1, y2. Okay, and now we can see that if we are on the line, this equation will be true, and I'll just rearrange this. So I'll formulate this as an error function, which depends on the point x and y, and we have okay, a little messy there, but this would have to be 0 to be exactly on the line, because what I've done here is I've subtracted that y from both sides. Okay, so we can formulate this with coefficients. These are constant numbers, if it helps. And yeah, so if I look back at my diagram, I'm trying to solve for the root of this equation. I'm trying to approximate the root of the equation. So everywhere that error function is equal to 0, we are on the line. And if I just look in the y, everywhere y is above the line, whoops, that should be a y there, shouldn't it? Everywhere a y is above the line, this expression here will be making the whole f negative. So here we have f less than 0, and everywhere y is below the line, we have f greater than 0. Okay, so now if we were to look at this again, the question is, given that we are at some point, let's step across in the x value, in the x coordinate to the next point, and then we'll either stay where we are or increase our y value. So we are choosing between the current x coordinate plus 1, current y coordinate, and the current x coordinate plus 1. Sorry, that plus shouldn't be in the subscript. That should just be literally adding 1 to the x coordinate, and the current y coordinate plus 1. That's our choice. That's our choice. So the way this goes is we have a decision parameter, which is defined as the value at that the midpoint. between those two. So the next x coordinate, but then the next y coordinate plus 1/2, and then minus the previous point that we plotted. Okay, now there are two choices for this. There are two choices. Either d is bigger than 0, in which point the midpoint is too far down. Okay, so if we were plotting along and then we had to choose between this point and this point, and our midpoint was that's right. I'm just thinking. Well, this is a bad example, but anyway, well, have a look here. So let's say our midpoint between these 2 points is down here. Well, then f would be bigger than 0, and then this whole expression would be bigger than 0, in which case we would plot the point above. So we'd plot xk plus 1, yk plus 1. And then if d is less than 0, we don't change. So to go to another scenario, let's say we're choosing between this point and this point up here. So we look at our midpoint. That expression is less than 0, and so it's on the bad side, and we plot the lesser y coordinate. So in a nutshell, that's the decision that we need to make. But what does this actually evaluate to? Well, the truth is it's not that bad. So if we were to have a look here, we have, again, our decision parameter d is the difference between going to the next x coordinate. Okay, difference between that and the point that we just came from. So subtracting the previous value. As we can see, the c is going to cancel out, the ax is going to cancel, the by is going to cancel. So this gives us a plus b on 2. And yeah, that's a constant value, so that's pretty nice. So then if we go back and look at the actual values, we have that a was delta x, b was negative delta y, so we have negative delta y on 2, and that is the decision parameter that we work with. Now, that's fine, but what we can do is we can also track the change in decision parameter. So instead of continually plugging things in, we can say that the change in decision parameter, if we plotted x, k plus 1, would be, well, the next point from there would be xk plus 2, yk has already increased by 1, then we increase it by another half on top of that, so that is plus 3/2, subtract the previous point, which would be, or subtract the value at the previous point, so that would be yk plus 1. And this is a little messy, but it comes out in the end. Okay, so then if we look here, we have this xk plus 1 subtracting here. That just leaves us with 1. And then yk plus 3/2 subtract yk plus 1/2 just leaves us with 1. And c completely cancels out. So this gives us a plus, well, a minus b. So that is dx. Yeah, dx minus dy. Whoops, what am I? I read the wrong minus here. This term here was completely cancelled. It's this term here plus b. Okay, good. So On the other hand, if we plotted xk plus 1, but just yk, then our decision parameter would be that one there. I'm sort of running out of room on my page, but I hope you can see that the y dependence just isn't there anymore. That's all going to cancel out. So this will give us just dx. So what we do is we start with an initial decision parameter. We make a decision about which point to plot, and then that decision parameter increments by a certain amount based on which point we plotted. But there's still an issue. The issue is we have this dy over 2, and the whole point of the Bresenham line algorithm is to recast things into just integer operations, because integer operations typically are faster than floating point. So this comes down to, we can modify this with the fact, the whole decision was whether the decision parameter is greater than or less than 0. This is the same thing. Now, this is equivalent to saying 2 times the decision parameter is greater than or less than 0, or equal to 0. So what we can do is, for our initial value for d, we can take 2dx minus dy. And then for our for our change in d, we can take 2dx minus 2dy. And then again here we can take 2dx. So there we have it. There are some other edge cases. Now if our line is going down, then instead of going yk plus 1, just go yk minus 1. And we'll also have to flip around dy. And what else? If we've got a steep line instead of a shallow line, then everything will be flipped around. Here for our decision parameter, we'll have an initial value of 2dy minus dx, and we'll do the same thing. So let's hop into the code and have a look at how we'll implement this in general. Get into gameplay. Okay, so let's get into it. Here's the project, and for this first stage, I'm just going to do horizontal and vertical lines. These don't need any particular algorithm, they're very straightforward. We'll just open up the header for the engine that's in the view folder, and I'm going to declare a bunch of these functions. So I'm going to say, alrighty, this function will be void, and it will just draw a horizontal line. Now what we'll need here is we'll need the color, which will take 3 floats. And then in addition to that, we'll need the points to draw between. So a horizontal line will go between 2 x coordinates. So we'll have x1 and x2, and it will be at a constant y coordinate. Okay. In addition to that, I'm going to add an AVX2 version so I can do the same thing but 8 pixels at a time. Otherwise that'll be exactly the same. And I'll make a draw vertical line. Okay, cool. So let's now head into the source file, engine.cpp, and we'll go ahead and define these functions. Okay, so the first one is I want to I've messed this up, sorry. With the vertical line, we have a constant x coordinate, and then we're varying the y coordinate. Of course. Okay, so where was I? If we look back at clearing the screen, it's very similar. So what I'll do is I'll just grab all of this code, drop it down. So the first thing I do is I get the current frame that I want to draw to, and then I convert the color into an array with 4 bytes. Then what I want to do is I just want to clip these screen coordinates. So I'll go x1. So I'll clip it between a maximum of 639 frame width -1 and a minimum of 0. Okay, now I'll do the same thing with the x2 and the y. Okay, excellent. So now my coordinates are valid. Now, what I'm going to do is I'm going to loop along. So I'll make a variable. I'll start that at x1. I'll keep going until I reach x2. And I'll increment it. So we're stepping left to right. And I'll say, okay, we need the pixel location that we're writing to. So make this variable pixel, and that is, well, we'll be doing this. So we go, we do the scan lines going down, then add the x coordinate. Now, if you look at the way we're using this down here, we multiply that by 4 and we add offsets each time. So let's go ahead, and we can think of this as, taking that memory location and splitting it into 4 parts for each of the bytes for each of the channels. Okay, so now down here we can just go, oops, that's already done for us, so just go pixel and then pixel plus 1, pixel plus 2, pixel plus 3. Okay, excellent. So that is drawing a horizontal line. Now let's go ahead and do the same thing, but with AVX2. Okay, so this will actually be very similar to what we just did. So I'll just grab that. Now, what I'm going to do is I'll have an exit condition, because there's no point setting 8 pixels at a time if the function is being called to only draw 4 pixels. We need to have a significant amount of pixels to draw, otherwise just do the other method. So we'll say, okay, if x2 minus x1 is less than 16, we'll say, then just go ahead and draw the horizontal line. And that's it. Okay, so we get to this point here, that means we do have a significant amount of pixels to draw. That's fine. So again, we get the frame, we convert the color, clip the coordinates, but then I want to set 8 pixels at once. So I'll say, okay, I have this 256-bit wide variable called block, and I'll set them all to 1 value, packed scalar, which it means different things in AVX2. A float doesn't really mean a float, it just means raw data. But anyway, I'm getting ahead of myself. This wasn't really the focus of this video. So we'll take the color, interpret that as a pointer to a float, so set the stride to 32, and then dereference it, so grab 32 bits and send that in. Okay, cool. So now I want to know a few other things. I want to know the pixel count. Actually, maybe I don't need that one. Okay, we won't use that. Well, I want to know the start pixel, so this will be doing the same calculation as before, just based on x1. And then I want to know the start block. Because let's say, for instance, we're drawing a line starting at y equals 0, x equals 3. well then our start pixel is 3. But we want to know which memory location is that in. Divide all the memory locations by 8, and that will sort of be it. So if we take the start pixel, divide that by 8, but then if we're starting at pixel 3, we don't want to start at block 0. We want to just add 1 to be safe, so that we'll actually start writing at block 1. So start writing at pixel 8 from there onwards. Anyway, so then what I want is the end pixel. Which we'll do just like that based on x2. And then we'll get the end block. So again, divide by 8, but it could be that we've gone too far. So let's say we're ending on pixel number 25. 25 divided by 8 is 3, but that's setting pixel 25 plus another 7 pixels that we don't need. So we'll just dial it back by 1. So I'm giving myself a safety margin of up to 16 pixels, and that's why I've chosen this condition here that it has to be less than 16 to actually enact this function. But the only other thing we need to do before we jump into the drawing is get a pointer to the screen as an array of blocks. All we need to do is interpret the color buffer as an array of MM256s. So get the frame, color buffer data, get the pointer to that. Yeah, there we go. Okay, cool. So what I'm going to do is I'm going to, instead of X, I'll just have pixel. I'm going to start that at start pixel. And I'm going to run that up to, if I take start block times 8, that would be the start of that block, literally. There we go. Okay, so that's setting those pixels for the first few, and then what I can do is I can start looping through the blocks. So this will set the first 8 pixels and then start stepping through 8 at a time. Then after that we'll set the last 8 pixels. So I'll have an integer I. So just go from the start block to the end block, and we'll set this. So we'll say blocks I equals block. So there we have it, and then we'll go ahead, do the same thing, set the last 8 pixels. So we'll start at end block times 8, run up to the end pixel, and increment. And yeah, that will set the last 8. Okay, so I know this AVX2 stuff might be a little esoteric, but it does speed up the code. Why not? It's for free anyway. So let's go ahead and close that down. Now the last one we need is this vertical line. So let's jump in and have a look at that. Okay, and let's grab all the code from before. Right. So again, we get the frame that we want to draw to, we convert the color, and then we just clamp the values. So here we'll have X between 0 and width, and then Y1 between 0 and height, and Y2 between 0 and height. Okay, so now we'll loop based on Y. Loop based on Y, get the pixel location, and then set the 4 bytes within that pixel. Okay, excellent. So I'm not going to explicitly test these, but there we have it. Those are the drawing functions for vertical and horizontal lines. Okay, so we've got horizontal and vertical lines. Let's have a look at just doing lines in a naive algorithm. So we'll just head to the header, and there are 3 functions I'm going to write. First one is draw line naive, and just the same as before, we'll take red, green, blue, and now we'll take 2 x coordinates, x1 and x2, and 2 y coordinates. Okay, and the other 2 are the actual drawing functions. So this top line will be sort of like a hub. It will look at some parameters and decide which drawing function to call and how to call it. So I'm going to have a shallow line and a steep line. Yeah, there we have it. So let's take these functions and implement them. We'll go to the source file, paste that in. Okay, so first of all, we might just have a horizontal or vertical line. If the x1 and x2 coordinates are equal, then we're drawing a vertical line. Now we want to draw this vertical line from bottom to top, so it makes the loops nicer. So if our y1 is indeed less than y2, then no worries, we can draw the vertical line, RGB y1, y2, no worries. And we'll just take x1 as our x coordinate. It really doesn't matter, they're both the same. But otherwise, we'll have to flip this around. So I'll just flip the y coordinates around. This is the case where we said draw a vertical line, but actually we put the input in the wrong order. Okay. So we can do that and then return. We are done. Now another case here is if our y coordinates are the same. Okay, and if our y coordinates are the same, then we want to draw a horizontal line from x1 to x2. So I want to make sure that we are going left to right. In other words, x1 is less than x2. I'm going to use the avx2 function to speed things up. We'll go x2, y1. Okay. But if this condition fails or doesn't pass, then we'll just need to swap around x1 and x2. And you'll see a similar theme here. We'll be doing a pretty similar thing in all the other drawing functions. So then the next question is, do we have a shallow line or a steep line? So we'll say we want to get the, what is it? The y difference and the absolute value of that. So in this case where dy, the change in y, is less than the change in x, then we want to draw a shallow line. Now that shallow line is going to have x as its independent variable, so we want that to run from left to right. So we'll do something very similar up above. Yeah, draw a shallow line, x1, what's the order here? x1, x2. Ooh, I don't like that actually. I'm going to change that around. I'm going to do x1, y1. Okay, but if this isn't the case, if our x1 is greater than our x2, no worries, we can still do this, let's just flip those points around just to make sure that our line is going from left to right. Okay. Now, if this isn't the case, then we can draw a steep line. But with the steep line, we can get rid of this condition. The return is ensuring that if we get to this point, it's fine, we are in the right spot. Our y coordinate is going to be our independent variable, so we want that to go from bottom to top. Actually, top to bottom if you look at the coordinate system. But anyway, we want it to run from a small y to a large y. And yeah, that is our little control function. So it selects which line function to call and how to call it. Okay, excellent. So we can close this down and we can have a look at the shallow and steep lines. So if I go down to the shallow line, this will be very similar to the vertical line function. Let's grab that one. Okay, so what are we doing? We grab the current frame, convert the color, of course, but we're going to need to do a few geometric things. So I'll make a variable called dy dx. That's just the quotient there, and then I'll clamp all of the variables. And you could be saying, hey, wait a second, isn't it a bit weird? Like, isn't this going to mess with dy dx? And my answer to that is yes, 100% it's going to mess with dy dx. So we really shouldn't be relying on this min-max clipping. We should be doing our own clipping, which we'll get to in a future video. Okay, so hear dogs out there? Anyway, where was I? Where was I? Okay, so we'll go take y, start that out at y1. And this is just for convenience. I'm going to keep track of this in pixel form as well. And I'm also going to keep track of the pixel that I'm writing to. Okay, cool. So then we'll pop into the loop. So we'll run x from x1 up to x2. Okay, so we'll cast that float to an integer, and then we'll do the regular calculation. Okay, then these lines here will set the color. All we need to do down below is increment y. So we'll increment it by dy dx. And there we have it. That is a shallow line. So then we can take this code and use it again in the steep line. Okay, so again we get the frame, convert the color. Now instead of dy dx, I'm going to be incrementing x with dx dy. Go ahead and clamp the values, that's looking fine. And then now x is the one which will be varying. So I'll have screen x, and now I'll loop in y. So y has the fixed increment of 1, x has a fixed increment of dx dy. Okay, so I go ahead, cast this out to an integer, and then I can do the same calculation. This is all fine. And then all I need to do at the end is increment x by dx dy. Okay, so let's go back and start testing this. So close all of that down, and I'll just go to my app that's in the control folder, go to the header, and I'm going to give this a function which I'll just call lines test. Okay, so then what I'll do is I'll go to the source code app.cpp down to the run function, and in between clearing the screen and presenting, I will call my lines test. The reason I've got this is so that later on I can quickly just comment things out, run different functions and stuff. So yeah, it's all good. Okay, so now I'm going to tell the engine to draw a bunch of lines. So what I want is, let's go draw a shallow line with a positive slope. So I'll say, all right, graphics engine, draw that. I'm going to make this a teal color. So I'll go one in the green, one in the blue. Now for my x1 and x2, I just need my x separation to be bigger than my y separation. So I'll go x1 of 20 pixels, y1 of 32, x2 of 420, so that's a dx of 400, y2 of 128. So let's go ahead and run this, look at what we've got. I just realized, sorry, I've got it in release mode. Needs to be in debug mode. Again, as I said in the previous video, the OpenGL version, it doesn't matter, release or debug, but the Vulkan is unstable in release for whatever reason. Okay, so there we have it. Something doesn't look right there. Okay, let me just double check that. Should absolutely not be doing that. Okay, so draw line naive. I forgot to reorder this one. Okay, y1. Okay, let's give that a go. Okay. Okay. Look, I promise I'm not doing this on purpose. Okay, so let's sort of, yeah, print out. And then I'll just go back to my app. This is actually a really good exercise because often when I was developing this, I was going through exercises like this. So instead of running this every single time, we'll just run it once, print out the info, check that we're getting to that function that we expect to get to. Yeah. Yeah. Okay. Okay, yep, so we are getting to that function. That is fine. Okay. Okay, so we are definitely coming into this function, which is what I would expect. Oh, okay. Okay, this is a good little exercise. So, can you see where the error is? It turns out the error is in the calculation of this dy dx. Because we're using integer values, won't work so well. It'll try to do integer division. What we need to do is convert one of these into a float, and then it completely, oh sorry. We need to, of course, get rid of the return statement. And it's completely messed up. Okay. Okay. But that's fine. We can do this. Should I be using screen Y instead of Y? Yes, I absolutely should. Okay, so there we have it. So the issue is I was using a float to set an array position, which is why it was sort of acting randomly. That's fine. Okay, so we can just go down to the naive function and make sure, sorry, the steep line function, and make sure that we are using screen X here as well. Okay, excellent. And yeah, so I'll just head back to the app and keep going with this test. So I've got that. Now let's make a steep line with a positive slope. So I'll take the same, and I'll just give this a larger y coordinate. So we have an x separation of 400, a y separation of 596. And again, we have the same issue because I forgot to fix that. So again, the issue is dx, dy. We're doing integer calculations, so it's a little bit off. So we'll just go back to the steep line, put that float in there, and there we have it. Okay, so now we have shallow lines and steep lines, positive slope, which means y is increasing, they're going down across the screen. I'm pretty happy with that. Okay, so now let's go back to the test, and we'll set this up so that we have negative slope. And the way we'll do that is simply reversing the reversing the x coordinates, but not the y. Okay, give that a go. Yeah, and now we've got the same thing mirrored backwards. So we've got negative slope, we're coming up the screen, y is decreasing, and it's handling this just fine. Okay, so that's all well and good. The next point is we'll look at Bresenham's line algorithm. All right, so we've got the naive algorithm working. Let's have a look at Bresenham's line algorithm. We'll head to the header, and I'll go ahead and add in some more functions. So we'll have draw line Bresenham, and then likewise naive becomes Bresenham, and same with the steep. Okay, cool, excellent. So now we can head over to engine.cpp and grab everything in this naive line drawer, because really we're doing the same thing. We're making decisions. The algorithms, they depend on the same thing. X always needs to go from left to right. Y always needs to go from a low number to a high number. So where was I? So we have this Bresenham. Now, vertical line doesn't change, same thing. Horizontal line doesn't change, same thing. Now, these ones, shallow and steep lines, we can go ahead and change that. Okay, yeah, fair enough. Okay, so let me just pop down, and I'm actually going to, I'll start with the same function. So we'll get this one here. Okay, so same steps. Grab the frame, convert the color. I'm not going to do this. Get rid of that. Clamp the X and Y. Now I'm going to get the deltas. So I'll have int dx And I'm going to have another variable which I'm going to call y increment, and that's the amount that I want to increase y by if I so choose. So we'll have that one, and then we'll say if dy is less than 0, then flip these around. So change the y increment to -1 because, well, if we should be decreasing y, then change the increment to -1. And then this dy is used in the decision parameter, and so that needs to be flipped around as well. Okay, right, so then I'll have the initial decision parameter d, and that is, oops, 2dy minus dx, and then I'll have the changes in d based on what I choose to do. So I'll have an increment, a change in d if I choose to increment the y or decrement, and that is 2 times dy minus dx. And then I'll have a change in d if I don't increment 2dy. Okay, excellent. So we don't need any of this. We just need the pixel position that we're going to draw. Okay, so as you can see in the initial step, we are taking x and y at x1 and y1. So we'll go ahead and draw the pixel. There we go. And then we need to make some choices. So we'll say, okay, if the decision parameter d is bigger than 0, then we'll increment. So we'll say change the y value and change the parameter d. Okay. Otherwise, well, the y value stays the same, and then we just change the d parameter. So there we have it. That is our shallow line function. So let's go ahead and implement the steep line function, and then we'll test all of it. Okay. So very little of this needs to change. Guess we'll be changing the x value based on dx. And then in here, these will be flipping around, so dx and dy play opposite roles. Okay, and now y is the loop variable, which we control, and x is the decision variable, which is decided according to d. So again, we go ahead, we plot the first pixel, and then we say, okay, well, based on our decision parameter, we change x, or we don't. And that's it. And that's it. We're just flipping the role of dy and dx. Okay, so let's go ahead and call this. So we'll just kind of close that down and then head to our app, our line test, and we'll do the same stuff. But here I'm going to make these lines sort of a purple pinky color. So just to see that they're different. Okay, excellent. And I also want to shift things across by, I don't know, 200 pixels. Okay, cool. So if this is working, we should see a bunch of teal pixels, lines, and the exact same lines but shifted across and purple. Let's give that a go. Fingers crossed. No promises. And there we go. Excellent. Okay, so this is all well and good. These lines, they look pretty similar. They're meant to look similar. The question is, how does performance differ? Because the teal lines are using floating point operations and the purple lines are using integer operations. Now guys, I really want to know how this is on your system, because on my laptop, I was getting a significant difference. I was getting 140 microseconds to draw the teal lines versus 110 microseconds to draw the purple lines. So about a 30% performance increase. But then on my system right here, my desktop, I'm getting a very little performance increase. So it's just interesting to know. Let me go ahead and craft up a test for this. So I'll just go in here and define a few things. I'll have okay, so I just set up some render times, and then in my app, I'll just pop up the top and I'll import Chrono to do timing. Okay, cool. So what I'll do is go with I don't know, I'll go with 1,000 samples. So I'll say, oh yeah, I forgot about that. I'll make another variable called trial count. So now I'll say, okay. Righty, so I'll just take the time to perform these operations, and then what I'll do is change render time A, so 1,000th of this time. Yeah, get it to microseconds. Yeah. Okay. Cool. So that is getting the 1,000th of a sample, basically. And we'll do the same thing with this one. Just double checking, and we'll increment render time B. Okay. Now, otherwise, now just for visual purposes, I'm going to actually draw all those lines, but I'm just not going to change I'm not going to update the timing records. So once this is done, we'll just see the lines on the screen, and in the terminal, we'll get the performance data. Good, so we've got the time to render under both algorithms. Now, just so that it's not continually printing this out, I will go to the app and make a another variable called logged, and then I'll go back and I'll say, well, if we haven't logged that performance, go ahead and log it, and then yeah, mark that as done. Okay, so moment of truth. Let's fire this up. Okay, so whoops. We need to increment our trial count. Let's try that again. There we go. Okay, so like I was saying, on my other system, it's a massive difference. On this system, it's actually not too bad. So yeah, 30 microseconds for the teal lines, 28 microseconds for the purple lines, not dramatic. But like I said, I really want to know how this performs on your system because I'm curious. I'm curious. Okay, so yeah, there we have it. All right, so that's it. We've got some lines drawing on the screen. That looks nice. In the next video, we're going to use the lines to make a basic wireframe cube and have a look at projection systems. All right, so I'm looking forward to seeing you there. And yeah, have a good one. Bye.